Hi, this is Fiona French, and today I will be discussing Lab 1 Constant Velocity. Here's the table of contents, including the introduction, Newton's second law of motion, the experimental setup, the computational model, graphical comparisons, and the discussion. The main objective of this experiment is to apply Newton's second law of motion of the system to observe consistent movement of an object without any change in its speed or direction. We will assume that the net force is zero and neglect any opposing forces to depict the variance between experimental data and the computational model, to try and accurately describe various physical principles in the real world. Newton's second law can predict the trajectory of an object's acceleration due to two main factors, including the net force and mass of an object. There are two possible outcomes: either there's no net force and a constant velocity, or unbalanced forces will lead to an acceleration or deceleration in an object's motion. To our right, you can see the force equals mass times acceleration, and because there's a constant velocity, we can see that the net force will be zero. An object will move at a constant speed forever unless an outside force acts on the system, which will affect the vector quantity momentum. To our right, we can see the derivation that gives us the velocity final will equal velocity initial in the velocity update formula due to the momentum principle. One of our results was that the negligible forces led to discrepancies between predicted and measured data sets due to the real-world surroundings. Here's some additional physics concepts that may be needed to fully understand this lab, including Newton's first law, which describes how an object in rest or motion will remain in such a state until acted on by an outside force, the position update formula, which is put in our starter code, and some free body diagrams, which show the difference between a constant velocity, having two forces acting in different directions at the same magnitude, and non-constant velocity, which does not show that. For this investigation, the system included the rolling object, which was a shallot, and the surroundings were everything else, including the gravitational force. Some important notes to make were that all frictional forces and air resistance were considered negligible because the net force was zero, and the displacement was only measured in the x-component, whereas the y and z were completely ignored. For this procedure, we recorded the motion of a shallot rolling in one direction at a constant speed on a flat surface. This video was put into Tracker to collect quantitative data, including the time and position of the object. The starter code was edited within GlowScript to add initial conditions and physics equations to receive output for a theoretical dataset, and then we graphed the experimental setup versus the computational model to compare trends. This video shows how I tracked my motion. On the right, you can see the graphs, and you can also see all the data points, which were chosen by the center of the ball. For our computational model, we actually needed information from our tracker data, including the observation start time, end time, initial position, and velocity. So within our first two frames, to calculate our velocity, we needed to subtract the position initial from initial final and divide it by time to get 0.152 meters per second. Our computational model consisted of editing starter code within GlowScript to meet our initial conditions. The object's initial position and velocity vectors were inputted from our experimental conditions in the slide before this, and delta t was changed to 0.033 due to our frame rate being 30 frames per second. And the mass can be changed to accurately depict the object, but it's not required because mass has no effect on velocity of a moving object, so I just kept it as 1. And to our right, you can see my graph, which is position versus time. Another couple of things were changed within this computational model was t, because our change in time for this experiment was 1.402 seconds. And then I added the position update formula and the velocity update formula, which were needed to calculate the times and positions of these objects at certain intervals. This graph shows the comparison between the position and time of our experimental dataset and our computational model. The gray line represents the predicted dataset, whereas the blue line represents the observed dataset. We can see that the predicted dataset is way more linear than our actual data due to it being theoretical and not real forces acting on it. The deviations between the datasets, the experimental and predicted, may have been due to sources of uncertainty, including negligible forces. For example, the force of friction and air resistance acting on the shallot skin roughness may have led to a higher chance of non-conservative forces acting on the system. There was also issues with the center of mass. Inconsistencies within Tracker when choosing the center may have led to errors in data precision. And also, the initial push velocity may have been quicker, and the shallot may have been accelerating at the beginning and slowed down at the end due to the initial force being exerted at the beginning and not throughout the entire movement. Additionally, there may have been issues with coding. So the what if the axes were flipped? The slope of the line would actually change from the positive direction to the negative direction, but the magnitude would remain the same. When I initially recorded my video, I had the object moving from right to left, but I realized that my slope was negative, so I mirrored the video to be in the positive direction. Essentially, changing where the axis is located within Tracker will make the object either move backwards or forwards, or in the opposite direction you want, or the right direction you want. The rate of change will remain the same value, and the only thing that will change is the direction. Is it possible to determine push and pulls? So the net force, which is described as push and pulls, cannot be determined alone from this experiment. The computational model can create the perfect scenario with no net force acting on it, but in reality, we have outside forces that will affect the motion, which can be seen in the difference between the graphs. There will be friction and air resistance, which will lead to accelerations and decelerations within the change in momentum acting on the